Hello guys. Okay, so now I'm going to show you how do we actually find the expressions of H field that from the structure of solenoid. So as we know that the solenoid actually is structure that made by the multiple number of line current in loop. So let's see if you can see from these diagrams. So this is solenoid that have n number of loop, and the loop of current actually in circular loop. So if we add up everything, so actually can actually create a structure called as solenoid. So let's say I'm refer to the example or problem given in statistical book. If you can see from your book, problem 7.4, page 302. So this question asks us to refer to the figure 7.9, so as given in the book. So the figure given in 2D, now I show you in 3D. So that's how the solenoid looks like. So now we know that the A given here, the A actually the radius of the solenoid given as 5 cm, and then it has number of turn about 2000 number of turns, and then it has the current 50 milliampere, and the current actually flowing in positive phi direction. Let's say this one, right? There's current directions in positive phi. So now we are going to find the H at multiple positions as shown in the book. But to make it easy, I would like to show you how do we find the equation that can be used to any positions. So you can find the general equation. So that's easy for us to just substitute the value of point of interest later on. So now let's say we want to find the H field anywhere along or even inside or outside the solenoid. You can find the value. Let's say I want to find the value of H at this upper point. Let's say at the Z point. Okay, I want to find the H, the point of interest at here. Okay, so again, so this actually a structure of solenoid is made by the multiple number of line current. So now actually they are becoming a surface current. Okay, no longer line, because line is single loop, but now solenoid we have a multiple loops of line, so we can actually consider as a surface current density. So as we learned last time in our lecture, we know that the Js is our surface current density for this structure of solenoid. So it can be obtained from the equation of current over length, isn't it? Because the Js unit actually ampere per meter. However, this case we have number of n. So now this case we have n is something value. So we have to add this n term up in front here. So it shows that the current not only single, but we have multiple current in loops, right? So just multiply between n and I over the L. So that should be the equation of Js. And since we know that the Js now, guys, flowing in the phi positive direction, so we can simply put here become a phi component. So now here it become ampere per meter. That's our surface current density for this solenoid structure. Okay, again, so since this is a very small structure, infinite structure, so you can simply use BSL to solve the problems. So based on BSL from here, DH. Okay, now we are dealing with our JS, so must take the current element from JS. Okay, now no longer in ILDL, so take this current element from the JS here. So let's say this is my sample of current element. So that's going to be our JS DS. Okay, that's our current element for the case of surface current density. Okay, now put the value inside the BSL equation. From here you can have the JS vector DS times R component over 4 pi R cube. Alright, now we have already DS here. So I want to find now the R vector that joining from the sample or current element to the point of interest up there. So let's join them. You can see. So that's a vector that joining from current element to the point of interest. So you can find the R vector by adding or add up the two vector in R and also in Z up here. Okay, so let's say guys, this current element is positioned at this point. Let's say the A, the phi and Z prime. You see now why I put A? Because now the solenoid, the radius of solenoid is being fixed at A, so you can put simply A, don't put R. Okay, so now I put A because referring to the solenoid radius, and the phi is variable, could be anywhere within this solenoid area, and the Z prime and also a variable, so between 0 to L. So here become your, and now it's your position of sample or current element should become Z prime. It means that this position of sample guys could be anywhere along the solenoid with from 0 to L, so could be anywhere, it's up to you. So that's why you put here Z prime. So in this case we have two variables that varies. Actually the first one is your phi, that could be anywhere from here, could be there, back, front, and also for the Z prime also a variable, could be down here, in the middle, up there. Okay, and only the R remain constant, alright, because the radius is kept constant here. Okay, now so let's find the R vector. You can see from here the R vector can be obtained from these equations. The first one is negative A R component, because readily inward, negative A R component, then plus here Z minus Z component, Z minus Z prime, Z component. Okay, that's our R vector, the vector that joining from sample or current element to the point of interest. So now put this value R here and the GS here into this BSL equations. But before that, what is our DS for this case? You know, right? This DS for this nickel actually become your R d phi dz, right? So here you can have the DS here as well. Actually, A d phi dz prime again, because this ds guys refers to the sample or to the current element whereby located at Z prime, so must put prime there. Okay, so now let's put all this substitution, the R, ds and gs into this BSL equations. What you have finally, so the dh here become the ni over L phi component, and then the ds here A d phi the dz prime, and then cross negative A R component plus Z minus Z prime Z component, and over 4 pi, and here we have A squared Z minus Z prime squared 3 over 2. So that's after substitution for the JS, for the R vector, and also for the DS. Okay, so now again we are dealing with cross product between phi cross R and also phi cross Z. So let's do it together. First one here is a phi cross R and also phi cross Z. So let's do this simple approach to find the output of this product. The first one here, let's draw here a Z, R, and a phi. The R cross phi, the output is Z. The phi cross Z equal to R. The Z cross R equal to phi. Now again, the phi cross R. The phi cross R, a negative Z. So we're going to have a negative Z component. And then again, phi cross Z equal to R component. Positive part. Again, since this is a symmetrical structure of solenoid, we can ignore this term R because they will cancel each other in R component. So we are going to ignore this term straight away. Becomes 0 because R, right? R component. So now let's proceed. So again, this one is your constant. Negative times negative got positive. So here the H, positive Z component, and then see A times A got A squared. So here Ni A squared over 4 pi L, and then integrations. For the first integration, we refer to this phi component. So d phi 0 to 2 pi, and then for the second integrations, refer to the dz prime. So here dz prime over a squared z minus z prime squared 3 over 2, and the limit for the z prime, if you see from the diagram, the z prime, the sample element or the current element can varies from 0 to L, right? So you can simply put here from 0 to L. That's the limit for the current element. So now you can solve this equation using table or formula given in textbooks. So let's proceed together. So here we have z prime and z component and I a squared 4 pi L. So I'm going to have 2 pi, right? And now this case we're going to have this one z minus z prime. Make sure in front got negative because we integrate over z prime negative, right? So put in front negative, and here a squared z minus z prime squared 1 over 2, and the limit from 0 to L. So let's substitute the value of 0 and L into the z prime parameter. So now we can simply, and don't forget guys, in front here we have a squared again, okay, a squared as well. So this one 2 pi, 4 pi got 2, so this a squared, let's say this one a squared cancel each other. So now let's proceed. So this is your z component and I over L. So here now we have z prime minus z. So what we have here? So the L minus z over a squared plus z minus L squared 1 over 2 minus, so this one we know that actually z prime minus z, so plus z, right, over a plus a squared z squared 1 over 2, right? Alright, so that's the idea so far. So let's proceed the solutions to the final form. of these equations, you can see that if you proceed the equation by substituting all the value, so the h here, as before, we have z component and I over 2L, right? And then brackets here, so the have the L minus Z, so the first one is L minus Z over the A squared plus Z minus L squared 1 over 2 plus Z the A squared plus Z squared 1 over 2. So if I want to find the H at the first one, let's say at the point of 0, 0, 0, it means that the Z here we put 0, 0. So at 0, 0, 0. So the H now becoming Z, and the N put the value of 2000, and the I put the value of 50 milli, right? And also the DL, we put the value of 75 cm or 0.75 meter, and then this one put 0, so we lost this term already. So now again here 0.25 minus 0. So here have and how about the radius? Actually 5 cm. So you can put here 0.05 squared plus 0.75 squared, and then square root everything, and here since 0, right, so plus 0 equals to 0. So you can find finally the H value at 0, 0, 0 becoming 66.52 Z component ampere per meter. Okay guys, so you can actually find the H value at any point along the axis of solenoid, either on the center here, either on the bottom edge, or even on the top edge, or even a higher positions. It's up to you. So you just find the general equation as shown here that can be used to find the H field at any positions that required by the equations. Okay guys, I hope you can try yourself. So thank you.